Before there is a mission, there is a team.
We are PUCRA, the Student Robotic Association from the Universitat Politècnica de Catalunya, based at the Barcelona East School of Engineering. Mission PHOENYX is our return to the European Rover Challenge, a project that brings together PHOENYX-II, our planetary rover, and IKARUS, our aerial exploration system. And to understand where PHOENYX is going, you first have to understand where PUCRA comes from. Founded in 2017, what began as a student initiative soon found its rhythm in competition, and in 2018 we discovered BEX Robotics. From that moment, BEX became part of PUCRA's DNA. In 2020, that path took shape as Tharsis, our first rover project for the European Rover Challenge. But just as the project was taking shape, the COVID pandemic changed everything. The rover never reached the field, the team went through one of its hardest moments, and the project slowed down. But that ambition never disappeared. In 2024, a new generation brought that mission back to life.
Today, Mission PHOENYX is driven by a multidisciplinary team of 15 students: mechanical, electronics, chemical, and software engineering, from bachelor's and master's students to PhD candidates. Each member brings a different skill set, but all work towards the same goal: to bring PHOENYX-II and IKARUS to the European Rover Challenge. Mission PHOENYX takes shape as a coordinated network. Mechanics give the mission its physical form, led by Oriol del Castillo. Electronics becomes the mission's nervous system, guided by Santiago Pallares. Coding gives the system its awareness, coordinated by Marc Redolat. Science gives the mission its purpose, with Judith Salvador coordinating the team. Beyond the technical systems, marketing led by Paula Olivera gives the mission its voice. Resources turns ambition into possibility, managed by Oriol del Castillo. And every mission needs a point where everything comes together. For Mission PHOENYX, Elena Villalba coordinates that connection. Different departments, one shared direction. One team, one mission. But why return to the European Rover Challenge? Because for PUCRA, ERC was an unfinished path. Mission PHOENYX was born to continue that path, to bring PUCRA back to planetary robotics, with more experience, a stronger team, and everything we had learned along the way. But because we know the ERC is an immense challenge, Mission PHOENYX did not begin there. The first steps we took was PHOENYX-I. At Center CEA's Spot Talent, we built an autonomous rover, won 2 major awards, and proved that PUCRA was ready for more. That is why PHOENYX-II exists. Before PHOENYX-II moves through the field, the mission is already alive on the ground. From the ground control station, operation monitors rover status, visualize live camera feeds, receive 4D LiDAR data, checks telemetry, and teleoperate the rover when needed. But remote operation depends on one thing: connection. To keep the ground segment linked to the rover, PHOENYX-II relies on 3 communication channels. The main 5.8 GHz Wi-Fi channel carries the video, 4D LiDAR data, telemetry, rover status, and remote commands. As a safety layer, an 868 MHz long-range point-to-point channel transmits basic telemetry, heartbeat monitoring, and fault information. And finally, a 2.4 GHz Wi-Fi channel provides fallback communication if needed. PHOENYX-II becomes the heart of the field operation. It is built as a modular ERC platform. The rover is designed to integrate 3 mission payloads: the ARM module, the laboratory module, and the deep sampling module. And at the center of this modular architecture, we can find the chassis, which becomes the backbone of the whole system. It supports the locomotion system, protects the internal electronics, and provides the main mounting interface for sensors, communications, external components, and payload modules. Inside the rover, the power system is designed for a rapid turnaround. PHOENYX-II uses interchangeable 36-volt lithium-ion battery packs, with integrated battery management and access through the rear compartment. To protect the electronics, PHOENYX-II integrates a forced air thermal control. Rear intake grills bring fresh air in, while bottom-mounted fans extract hot air downwards, reducing dust intake and maintaining stable internal temperatures. Each subsystem acts as an intelligent node, connected through a shared CAN bus and coordinated by the central Jetson Xavier AGX CPU. For high-level computation, the rover runs Ubuntu 24.04 with ROS2 chassis, connecting teleoperation, sensor processing, navigation, object detection, and autonomy. Once the system is built, it has to prove itself in motion. The PHOENYX-II locomotion system combines a 4-wheel swerve drive, with a differential rocker bogie suspension. Each wheel has independent steering and propulsion, giving the rover full omnidirectional maneuverability. To adapt to an uneven terrain, a top-mounted differential links both sides of the rocker bogie suspension, helping balance the rover's body, improve ground clearance, and reduce the risk of snagging on obstacles. At each corner, a dedicated steering module uses a custom cycloidal gearbox designed for efficient steering and low backlash. Traction comes from a brushless outrunner motors integrated directly into the wheel modules, paired with a custom TPU airless wheels that improve contact, obstacle conformity, and passive shock absorption. Safety is what makes PHOENYX-II reliable under real operating conditions. In an emergency situation, the rover can be stopped immediately through a physical emergency stop button. When pressed, the e-stop cuts the main power line, isolating the battery from the rover and stopping all rover activities. After that, PHOENYX-II cannot restart by itself. Recovery requires a controlled sequence. Release the emergency stop, press reset, and activate start. To make the rover stay visible at all times, PHOENYX-II uses a high visibility status light. Green indicates autonomous mode, blue indicates teleoperation, yellow indicates low battery, red indicates emergency state, turquoise indicates reset is required, and orange indicates that the rover is ready for the start command. While PHOENYX represents the fire of the team rising again, IKARUS represents the will to fly higher, to expand the mission's perspective from the air. To make that aerial perspective part of the mission, IKARUS is designed for both manual and autonomous operation. When direct control is required, the pilot can take over through a dedicated 2.4 GHz radio controller. As PUCRA's first UAV platform, IKARUS follows a risk-controlled design. Built around a proven S500 frame, it gives the team a reliable base to focus on what matters most for the ERC drone task: control, autonomous navigation, and perception. Custom mechanical parts mount and protect the sensors on the onboard computer, the flight controllers, and the battery system. At avionics level, IKARUS combines a Pixie-Hawk 6C Mini running Ardu Pilot for low-level flight control with a Raspberry Pi for high-level computation. At an autonomous navigation and landing, IKARUS combines IMU-Data, a flow-range sensor for altitude and ground relative motion, and an onboard camera. Visual information is processed in real time using MATLAB algorithms, allowing the UAV to detect the probes, estimate their position, and calculate landing coordinates for autonomous operation. Its propulsion system is based on 4 brushless motors driven by electronic speed controllers. By adjusting motor thrust in real time, the flight controller stabilizes the UAV, controls its altitude, and allows movement along its 3 axes. This gives IKARUS the ability to reposition itself, maintain stable hover, and approach landing zones with precision. From the ground control station, an emergency command can trigger an emergency mode and initiate a controlled auto landing. If communications with the GCS is lost, the same auto landing response is executed automatically, preventing uncontrolled flight. A rover is not ready for a mission until it can interact with the world around it. The payload system follows a plug-and-play architecture. Each module shares a defined mechanical, power, and communications interface, so it can be mounted, connected, tested, and replaced with the minimal downtime. At the center of the system is the arm module, a 6-degree of freedom robotic arm designed for teleoperation and autonomous manipulation. Through a quick release and end effector interface, PHOENYX-II can switch between task-specific tools. For maintenance and probing, the adaptive gripper interacts with switches, connectors, objects, and task elements. For astrobiology, the AstroBio end effector integrates a pH sensor and a liquid sampling interface to support science operations. For surface sampling, the surface sampling gripper collects and retains regolith and rock samples before transferring them into onboard containers. Once samples are collected, the laboratory module stores and characterizes them, with dedicated containers for rocks, regolith, and liquid samples. For subsurface exploration, the deep sampling module uses a vertical drill system to extract material from below the surface and deliver it to the onboard container. Together, the systems turn PHOENYX-II into a multi-role rover built to manipulate, sample, analyze, and adapt to the ERC missions.
PHOENYX-II is our return in motion. IKARUS expands our vision, but behind them, there is a team ready to rise.